And next, we are going to hear from Ritwik. So this will be our last talk from this session. And Ritwik Niyogi did his PhD in theoretical neuroscience and machine learning at the Gatsby Computational Neuroscience Unit at UCL, where he was supervised by Peter Dayan. And he developed a theoretical framework for real-time cost-benefit decision-making. And now he's currently a Sir Henry Wellcome postdoctoral fellow in the lab of Rob Rutledge at the UCL Max Planck Center for Computational Psychiatry and Aging Research. And he's also co-mentored by Nathaniel Daw at Princeton University. In his research, he applies machine learning and artificial intelligence techniques to longitudinal measures of vigor and energia collected on smartphones to identify at-risk individuals who are likely to develop depression, clinical depression. And so without further ado, please go ahead, Ritwik, and tell us about your work. Thank you.
Let's see.
Yeah, perfect. We hear you. We see your slide.
Chrome tab. Great. Not Chrome. Application window. Wait, hang on. It's not working as I planned it. So let's
Wait, did you just stop sharing? Because we saw your slides a moment ago.
No, sorry, that was me. That was the introduction slide.
Yeah. Sorry. Thank you.
So yeah, so if you go to toggle screen share, and you should be able to pull up your application window or just share your screen.
Got it. Can you see it now?
Awesome. Yep.
Perfect. Can you see everything is fine? Like you can see everything on the big screen?
Everything is fine. Yep.
Perfect.
Perfect. Well, thank you, Lana, very much for that wonderful introduction, and thank you very much to the organizers for inviting me to give this talk. It's really a privilege of a lifetime to be able to speak to this audience. Today, I'll be speaking to you about how dopamine makes you work harder, faster, and longer, and how it does so specifically by signaling the rate of rewards in the environment. And this is joint work with Nathaniel Daw, who, as Lana said, is my mentor. So, dopamine has dual roles. On one hand, we know from physiology literature that the dopamine firing and dopamine release signals reward prediction error. And reward prediction error is a key variable which drives trial and error reinforcement learning. On the other hand, from the pharmacology literature, we know that dopamine release drives motivation. Specifically, dopamine release increases vigor, that is a propensity to work faster, harder, and longer. What exactly is a learning signal doing in terms of driving motivation? How is a learning signal leading to motivated vigor? These two dual roles of dopamine were linked together by Gail Niv et al., who proposed that dopamine release signals reward rate, and possibly that this reward rate is estimated by filtering together or averaging together reward prediction errors over time. However, Niv et al. Had only access to pharmacological data, which is on a very, very slow timescale. Recent experiments have zoomed in on this timescale and have revealed a rich repertoire and rich dynamics of dopamine on a very fast timescale. This is the work done by Ali Mohebi et al. In Josh Burke's lab. And these experiments claim that the dopamine dynamics, these rich dopamine dynamics, signal expected return or the value. This talk will claim that this claim of Mohebi et al. Is not completely accurate. But if I'm going to say that's not completely accurate, how do we explain the fast timescale dynamics of dopamine with the slow accumulating dynamics of reward rate? This is what's going to be the crux of this talk. So let's back up a little bit and ask, what exactly is vigor in the first place? So vigor is the propensity to work faster, harder, and longer. Why do we even study vigor? Well, vigor or the lack of vigor, anergia, is one of the major symptoms of clinical depression. We know that dopamine increases vigor, but how algorithmically dopamine increases vigor and how is this implemented in the brain remains unclear. In this talk, I'll provide an algorithmic explanation of how dopamine mediates vigor and how it does so by estimating reward rates. What exactly is reward rate anyway? So reward rate is very simply the average reward per unit time. So suppose you're getting paid a very high reward rate of $1 million a second. Then your reward rate is that high value of $1 million a second. Alternatively, if you're getting paid a very small reward rate of 1 cent an hour, your reward rate would be 1 cent an hour. We know that dopamine makes one work faster. But why would you ever want to work fast? Working faster is energetically costly. The faster you go, the more energy you lose. What I'm going to show is that reward rate is a key decision variable in mediating vigor. When reward rate is high, you should go faster. And critically, it is also the variable that dopamine release or dopamine in the nucleus accumbens signals. And I'm going to claim that dopamine in nucleus accumbens signals reward rate by averaging reward prediction errors per unit time. How do we even model vigor? Let's think of it in a normative model, and let's look at the most essentially simplest model that I can think of, and the simplest behavior that I can think of. Suppose you have a rat which is running around somewhere in a chamber, in an experimental chamber, and a light comes on, after which it has to choose a latency and poke its nose into a center port. Some passage of time happens, after which it gets a reward, then it goes into the food port, collects a reward, wanders around until the light comes on, and then it chooses a latency, and it has to put its nose in the center port again. Some time passes, then it gets a reward, light comes on, it chooses a latency, pokes its nose in the center, and so on and so forth. The way we are going to model this is by what's called the semi-Markov decision process. Suppose the rat is in a particular state, and the state is just signified, does the light come on or not? Suppose the light has come on. Then the rat has to choose how fast to respond. Suppose the rat chooses to respond with a latency tau. Then it incurs a vigor cost for going quickly, and I'll explain this in a second. It also incurs an opportunity cost of time for going at this latency. It gets a reward, and it comes back to the same light on state. Once the light is on, it also chooses another latency. It incurs another vigor cost, incurs the opportunity cost of time, gains a reward, goes back to the same light on state. And this cycle goes on and on and on and on until the experimenter ends the session. If we can write down a cycle like this, or describe a task like a cycle like this, we can understand its dynamics from the concept of a reward rate. We can write down a reward rate. And what is the reward rate? The reward rate is the average reward per cycle divided by the time to complete a cycle. And if we can write down the reward rate, then we can write down the opportunity cost of time, which is just the reward rate times time. It is the average reward foregone by responding at a particular latency. Suppose you're getting paid $1 million a minute. Then by going slowly, you're foregoing on average a reward of $1 million a minute. If the reward rate is $1 million a minute, you really should be going as fast as possible. You're losing an opportunity which you could have which you could have taken that time, and you could have harvested in collecting more rewards and reaping the benefits of those rewards at the rate of $1 million a second, or $1 million a minute. By going slow, you're denying yourself the opportunity to get all these very rich rewards. So when the reward rate is high, the opportunity cost of time is high, you should be going as fast as possible. Let's describe this semi-Markov decision process algorithmically. So the net utility, or the Q value in reinforcement learning terms of choosing a particular latency tau consists of three things. Firstly, the reward that you get at the end, minus the vigor cost. And the vigor cost is inversely proportional to the latency. The faster you go, the more energy you lose, greater the vigor cost. Finally, there's the opportunity cost of time, which is just a linear function of the latency. Higher the reward rate, higher the opportunity cost of time, lower the reward rate, lower the opportunity cost of time. So now you can kind of sort of see that there is a battle between the vigor cost and the opportunity cost of time. The vigor cost basically says going quickly is costly, go slow. The opportunity cost of time, on the other hand, is going to say going slowly is costing you time, go quickly. So are you supposed to go quickly, or are you supposed to go slowly? Let's see how this model works graphically. I mean, this was the math. Let's explain this in a little bit of a graphical structure. In green, I'm showing you the vigor cost. It's inversely proportional to latency. If the latency is short, the vigor cost is very high. If the latency is long, the vigor cost is smaller. The red dashed line is showing you the opportunity cost of time. It's just reward rate times time. Now, suppose the reward rate is very, very high. You're getting paid the equivalent of $1 million a minute. At that point, your opportunity cost of time has a very, very steep slope. In order to find the optimal latency, we need to look at the net utility, or the net value, or the Q value of latency. That is the orange curve shown here. And the optimal value you can see is peaking at a latency which is very, very short. So when you draw latencies from this curve, your latency distribution will have a very short mean. On the other hand, suppose you're getting paid 1 cent an hour. Your reward rate is really, really low. Then your vigor cost remains the same, but your opportunity cost of time has a very, very shallow slope. In order to find the optimum, you take the red curve, you add it to the green curve, you get the net utility function. The net utility function here, you can see, has a maximum at a very large value. It's kind of almost hard to see compared to how peaky it is on when the reward rate is high. So when you draw this latency from this net utility curve, from this optimum, you find that the latency is very long. So just to recap, when the reward rate is high, your opportunity cost of time is high, you should be going as fast as possible. Your latency should be short. When your reward rate is low, then your opportunity cost of time is low. Then you should be going slower and your latency should be longer. Therefore, we predict, from the model predicts, that latency should decrease with reward rate. In fact, you can mathematically solve this model, and what you predict is that the optimal latency decreases with the square root of the reward rate. It is inversely proportional to the square root of the reward rate. But this is what the model predicts. Is this actually true in the data? To test this and to relate vigor with choice and learning, following on from Arif Hamid's work in Josh Burke's lab, Ali Mohebi, Jeff Pettibone et al. Designed a task in which, again, let's consider a rat is running around in a chamber. At a particular time, a light comes on. Then the rat chooses a latency. It pokes its nose in the center input. Now it has to wait for a go cue. A go cue comes on, and the rat has to choose either the left side or the right side. Suppose it chooses the right side, right port to poke its nose into. Then it gets a reward cue, which tells the rat that a reward is upcoming. The rat then runs to the other end of the chamber to the game, collects the food, runs back. When the light comes on, it chooses latency, how fast to respond, pokes its nose in the center port, waits for a go cue, gets a reward when it pokes its nose in, makes a choice, gets a reward when it pokes its nose into one of the side ports, collects a reward, and light comes on, chooses latency, and this process continues on and on and on and again. This is a condition in which we can apply a model, a normative model, which says that latency should decrease with reward rate. But does it actually do so? Here I'm plotting rewarded versus unrewarded trials. So long ticks show you rewarded trials, short ticks show you unrewarded trials. Let's take a condition when there are lots of unrewarded trials. If there are lots of unrewarded trials, then the reward rate shown here in black is going to be very, very low. If there are more rewarded trials, as you see here, then the reward rate is going to be higher. But what about the latency? Does it reduce with reward rate? Here in blue is the latency, and it is shown on a flipped axis. So this is a short latency, this is a long latency. And what you see is when the reward rate is high, the latency is short. When the reward rate is low, the latency is long. So the model does work. The model does make a correct prediction that when reward rate is high, your latency is going to be short and vice versa. But okay, how are we going to calculate reward rate? So I said, let's think about it once again. I said reward rate is average reward per unit time. What is an average reward per unit time? You just sum up all the rewards and divide by time. That's your average reward per unit time. But I'm going to claim that instead of summing rewards and dividing by time, you could sum reward prediction errors and divide by time, and you can get the reward rate. That makes no intuitive sense. So let's go into the math and see how it works. So let's first ask what even is a reward prediction error. And as my colleagues have before in the previous talks have discussed, a reward prediction error is the reward that you get at the current step plus the value at the next time step minus the value at the current time step. Now, if you sum reward prediction errors and divide by time, I'm going to claim that that is equal to a reward rate. So let's see if my claim is true. So let's add a bunch of reward prediction errors and divide by time. So sum of the reward prediction error is the reward at the current time step plus the value at the next time step minus the value at the 0th time step. Now let's look at the next reward prediction error. It's the reward at the first time step plus the value at the second time step minus the value at the first time step. And so on and so on and so forth. You keep adding reward prediction errors. Now let's look at this a little bit more closely and let's look at what happens to the equation. If you keep adding reward prediction errors, the value at the first time step cancels off with the value of the first time step here. Value of the second time step cancels off with the value of the second time step somewhere here. And the value of the last time step cancels off the value of the last time step somewhere here. And what you're left with is R0, the reward at the 0th time step, plus the reward of the first time step, plus the reward of the second time step, up to the reward of the 10th time step, or the last time step. That is, you're left with the sum of the rewards. What happens when you sum the rewards and divide by time? You get the average reward rate. So instead of starting with the average reward per unit time, you start with the average reward rate per unit time, and that is equivalent to the reward rate. Now, if all of this math was a little confusing and you got lost in the details, let me give you an intuitive feel for why this is true. And let's go back to the seminal work of Schulz-Dann and Montague. Suppose there's a Q, a CS, which predicts an unconditional stimulus. Initially, there is no prediction. This is an untrained animal. It's just receiving rewards. Then the prediction error at the time of the reward is just going to be equal to the reward. And critically, this is what dopamine neurons signal by bursting phasically at the time of the reward. Now, if you take the reward prediction error, remember the reward prediction error is equal to the reward in an untrained animal. You take that reward prediction error and you divide and add those reward prediction errors up and divide by time. What you get is basically going to be equal to the reward rate. Now let's look at the other extreme. You have a trained animal, and now the reward prediction error moves back in time to the time of the stimulus. And that is also what you see in the phasic firing of dopaminergic neurons. But the reward prediction error has not disappeared. The reward prediction error has just shifted back in time. And the value of the reward prediction error is still equal to the reward. So what happens if you average such reward prediction errors over time? You literally average, it's equivalent to averaging rewards over time. And what is the sum of rewards divided by time, or the average reward over time? It's the average reward rate. So therefore, you can start off with the reward prediction error and sum them, divide by time, and you can get the average reward rate. But what should you sum these rewards over? Do you sum rewards from time immemorial? No. A smarter way of doing it is by summing rewards by weighting recent rewards a lot more than rewards far back in the past. So you can, for example, use an exponential kernel or exponential filter by which recent rewards are weighted exponentially a lot more than rewards in the past. But you can calculate reward rate dynamically this way, by dynamically filtering rewards. But like I said, you don't need to dynamically filter rewards in order to get a reward rate. You can dynamically filter reward prediction errors and get back the same reward rate. And this is going to be the central theme of my story. I'm going to claim that dopamine signals reward rate by filtering these reward prediction errors. Does dopamine actually do so? So let's look at contrast two arguments about how dopamine mediates vigor. The first argument is from Niv et al., which says that tonic dopamine firing or release signals reward rate. And reward rate can be calculated by averaging together reward prediction errors, possibly. But the Niv et al. Story only has access to pharmacological data, and pharmacological data is very, 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 very slow. Recent experiments by Ali Mohebi et al. In Josh Burke's lab have zoomed in on this timescale, and they've revealed a rich, fast dynamics of dopamine. And what they claim is that these dynamics of dopamine going up and down isn't consistent with a slow changing reward rate signal. It is more consistent with expected return, which is the sum of current and future rewards. It is it connects more, it's more consistent with value. Let's look at the data on each of these cases. Firstly, what we see is when we look at the tonic dopamine baseline firing rate, we see that it is basically constant all throughout the session. Reward rate, on the other hand, fluctuates up and down. So while the reward rate goes up and down, tonic dopamine baseline firing remains the same. So tonic dopamine firing at least does not signal reward rate. And you can look at the high reward rate blocks, you can look at the low reward rate blocks, and you can see there is no difference in the tonic firing of dopamine neurons between high and low blocks. Tonic dopamine firing does not signal reward rate. What about the release? If you use microdialysis, then what you see is when the reward rate is high, the dopamine release is high. When the reward rate is low, the dopamine release is also low. So it does seem that the slow timescale dopamine activity, slow timescale dopamine release signals reward rate. But wait, I just said tonic dopamine firing does not signal reward rate, but tonic dopamine release signals reward rate. This sounds like a puzzle. What is going on? What Ali et al. Did was they zoomed in on this time scale, and they used the optical sensor D light in order to measure nucleus accumbens dopamine. What they found is dopamine actually has a lot of sub-second dynamics. It's not just a slowly changing signal well over minutes that we talked about before. On the above, I'm plotting the reward rate. Red lines show you rewarded trials, blue lines show you unrewarded trials. So you see a lot of rewards here, and what you see is the reward rate is accumulating or stepping up as more and more rewards are received. If you look at the D-light signal, what you see is that as the animal gets more and more rewards, the D-light baseline is also increasing, just like the reward rate accumulation that you see here. As compared to when the reward rate is much lower, you can see that the baseline is much lower in the D-light signal than when the reward rate is much higher. So it does seem like the D-light signal has some component of reward rate. But what you see that the D-light signal precedes the reward rate signal. So these increases happen before the reward rate signal actually starts accumulating. This led Josh Burke to claim that the D-light signal is actually representing the expected return or value, a signal which ramps up as it gets closer to the reward. But this is only true if we calculate reward rate by averaging rewards per unit time. I've been contending that reward rate can be computed by averaging reward prediction errors over unit time. So this is the same figure once again. And what we see here is that, again, what we see is and let me remind you, is that as the reward rate is stepping up or accumulating, so too is the baseline level of dopamine going up over time, as compared to when the reward rate is smaller and the baseline level is smaller. Now instead of calculating reward rate by summing rewards per unit time, let's calculate reward rate by filtering reward prediction errors per unit time. And what you see is that the D-light signal is locked to the reward prediction error signal. It's locked to the reward rate, and it's locked to a reward rate signal filtered over time. And so the reward prediction error signal filtered over time, which is the reward rate. So the reward rate, you can see, is basically you get a very nice match between the reward rate signal here and here. The delight signal is no longer preceding the reward rate signal as you had seen here. And let me remind you one more time, just to be absolutely clear, the baseline level, you can see that as the reward rate accumulates, the baseline levels of delight also accumulates. Finally, there's one last thing I want to point your attention to, that this delight signal is not just ramping up in time. What you see is a bunch of bumps. Here you have 2 bumps, here you have 1 bump, 2 bumps, 3 bumps. So this is not a ramp, this is a set of bumps. And what I'm going to claim is that these bumps reflect reward prediction error and the quick filtration of reward prediction error over time. Now let's look at what happens at the time of the reward queue. Before the time of the reward queue, what you see is when you order the delight signal by reward rate. So dark colors show you a low reward rate, a light colors show you a high reward rate. What you see is the delight signal scales with the reward rate. But this is the baseline signal, and you see it scales with the reward rate before and even after the reward queue comes on. Critically, this is not found in the baseline firing of dopamine neurons. So dopamine neurons the spiking activity of dopamine neurons does not signal the reward rate. However, what you see is if when you're at the time of the reward queue, this signal flips. In fact, there are higher excursions when the reward rate is lower than when the reward rate is higher. This is actually, I'm going to show, is consistent with the reward prediction error. When the reward rate is low, you are not expecting any rewards. So when you get a reward queue, your reward prediction error jumps up, and you get a massive reward prediction error at the time of the reward queue. When the reward rate is high, then you're expecting a lot of rewards. So when you get a reward, you're not that surprised. So your reward prediction error is low. Critically, you see that the dopamine spiking also shows this signal. So one possibility is, and the possibility that I'm shooting for, that I'm claiming, is that these spikes are averaged together over time to yield this dopamine release dynamics which scale with the reward rate. But if we are going to average together dopamine spikes, what time scale are we going to average those signals together over time, and what is the time scale of filtering? Suppose we filter dopamine bursts on a fast time scale only. In that case, what we find is that we find a phasic component of dopamine release similar to what we had seen in delight, but we do not, and that scales with reward prediction error, but we don't see the baseline accumulation scaling with reward rate. Now, on the other hand, if we just consider a slow time scale only, then we get the baseline levels of the predicted delight release scaling with the reward rate, but we don't have the phasic component scaling with reward prediction error. Finally, if we use multiple time scales, a combination of a short time scale and a fast time scale, then we can get the baseline release, the baseline delight dynamics scaling with the reward rate, just as we see in the data. And we also see the phasic component of the delight release scaling with reward prediction error, just as we see in the data. So dopamine filters reward prediction errors on multiple time scales. And that's what is seen in the data. Let's move on to the last thing that I talked about. So far, everything is consistent with dopamine filtering reward prediction errors with reward rate, and in order to get reward rate. What about the bumps? Here you see that there are 2 bumps. Here you see there are 3 bumps. Here you maybe see there are 4 bumps. How do you account for the bumps? Because that's not seems to be inconsistent with the reward rate story, and it's also kind of inconsistent with a continuous ramp that could be possible in the case of a continuous value signal. Let's go back to the Schulz-Dan-Montague work. So the time when an animal is not trained, you have a reward prediction error at the time of the reward. And that is what dopamine neurons fire to as well. But what I had said before, these reward prediction errors are basically equal to the reward. And these reward prediction errors are going to be higher in our case at the time of the reward cue. Now, if you overtrain the animal, or you train the animal sufficiently enough, the reward prediction error is going to march back and it's going to be transferred to the time of the cue. The size of the reward prediction error is going to reflect the value of the reward. So the reward prediction errors don't disappear. They just march back in time. They just move back in time. If we allow for some discounting, then the reward prediction error that you see at the time of the cue is going to be a little smaller than the reward prediction error at the time of the reward. Is this what we see in the data? That is indeed what we see in the data. So I'd already discussed what happens at the time of the side in, that's at the reward cue. You see a reward prediction error equivalent to what you would see at the time of the reward in the Schultz experiment. Now let's look at the go cue. What you see is a phasic burst at the time of a go cue. This is a cue which predicts a reward. So you see a reward prediction error at the time of the go cue and a phasic burst at the time of the go cue. Let's take this even one step further back. What about light on? What you see is a phasic burst at the time of the light on. Light on is further back in time than the go cue. So if you allow for some discounting, the reward prediction at the time of light on is going to reflect the discounted value, and the discounted value is going to be much less here at the time of light on than at go cue. So reward prediction at the time of light on is going to have a smaller value. As a consequence, the phasic burst at the time of light on is going to be shorter. It's going to be smaller. What about the delight signal? It's very simple. It's just the filtration of these bursts over time. So what you're going to get is these bumps. A small bump here, bigger bump here, biggest bump here. That takes care of the bumpiness in the signal. It is still just the reward rate which reflects the filtration of reward prediction errors over time. And critically, these bumps are going to get higher and higher and higher as you get closer to the reward, giving the shape of value envelope or an expected return envelope. But these are not expected return. This is actually consistent with the reward rate, which is found by averaging reward prediction errors over time. Is this the entire story? Unfortunately not. What we see is that in some aspects of the day, in some events in the trial, we see these bumps in the delight response without a corresponding increase in firing in the spiking. This is a bit puzzling. You could critic for us, and this is what we are working on right now. How do we understand this? One possibility is looking at when do these bumps happen. These bumps only happen to self-initiated actions. So you could assume that there is some timing uncertainty, and this timing uncertainty is leading to a reward prediction error, which is then creating a bump. But then why on earth is there not a reward prediction at the time of spiking? That's a quandary, and that's a puzzle that we're actively thinking about right now. Let's go on to the final bit. So I had said that dopamine signals reward rate by averaging reward prediction errors over time, or filtering reward prediction errors over time. But is this reward rate signal, which is encoded by delight or represented by delight, is this of any use for behavior, or is this just a signal which is floating around in the brain? I'm going to claim it is actually useful for behavior. So what I did was I took the log latency and I regressed with previous reward prediction errors and on previous trials. Then I took the delight response and I regressed it with reward prediction errors on previous trials. And what we observe is two things. Firstly, both have an exponential kernel weighting recent reward prediction errors a lot more than reward prediction errors in the past. And secondly, the timescale of filtering of reward prediction errors is the same across both for both delight and latency. That is, the reward rate signal which is signaled by delight occurs on the same timescale as behavior. So delight is useful. The reward rate signal encoded by delight is actually useful for behavior. That's a causal statement said with a correlational analysis. can we do a causal analysis? So let's do this thought experiment. Suppose you artificially deliver reward prediction errors at the time of a light on. What should an artificially delivered reward prediction error do? It should increase the reward rate. And if you increase the reward rate, it should lead to an increase in vigor or a decrease in latency. Is this what is actually seen in the data? And what we see is that this was an experiment, is exactly the experiment which was done by Arif Hamid et al. In Josh Berg's lab, in which on a 30% of trial, in which they express channel rhodopsin in dopamine neurons in the VTA, and on 30% of trials they stimulated these neurons. And what we see is when we stimulate these neurons, the latency to restart an action gets much shorter. That is, animals are much faster to come back to work when the laser is on than when the laser is off. What this is equivalent to doing is artificially delivering a reward prediction at the time of light on.
Sorry to interrupt, Ritwik. You have 2 minutes.
Yeah, I'm nearly done. So if you artificially deliver a reward prediction error at the time of the reward, what you see is the reward rate increases and your latency consequently decreases. Let's do the last thing. Let's do the last thought experiment. What if you, instead of increasing or artificially delivering a reward prediction error, what if you artificially remove a reward prediction or reduce a reward prediction error? That is, if you phasically inhibit dopamine neurons, let's say using halorhodopsin, then your reward prediction error should go down. As a consequence, your reward rate should go down. As a consequence, your latency should go up. Your latency should increase. And that is exactly what we see here. When you artificially inhibit these dopamine neurons, your latency should be longer than when you do not inhibit these neurons. So this reward prediction error causally leads to an increase in reward rate. This reward rate leads to an increase in vigor and decrease in latency. Let me just conclude. So what have I shown? I've shown that reward rate is a key variable which drives motivated vigor. We showed that fast dopamine release in the nucleus accumbens signals reward rate, and it does so by dynamically filtering reward prediction errors over time. And finally, we showed that fast dopamine in the nucleus accumbens signals reward rate not on a fast timescale or a slow timescale, but on multiple timescales. With that, I'd like to thank my mentor, Nathaniel Daw. I'd like to thank Josh Berg and Ali Mohebi, they who provided us with data and have been helping us. We've had lots of really fruitful discussions with them. And I don't know if they agree with anything that I've said, but they've been very encouraging all throughout this process. With that, I'd like to thank the organizers, and I'd like to thank you for your time and your attention. I'm happy to take any questions.
Great. Thank you so much for the talk. So I want to encourage people again to put questions on that stream one that you can see on the left, and then I'll relay the questions to Ritwik. Or if people feel more comfortable just asking their questions, that's perfectly fine as well. Does any, Ali, do you have any questions?
Maybe I can poke you, for a minute to start the conversation. That's fun. So, I mean, if this account that you suggested is true, that it might be like residues of reward prediction errors accumulating in time, right? You referred to some of Arif's experiments from like 2015, where he is artificially giving an optogenetic stimulation, squirting dopamine, presumably in the accumbens, right? And you would see a change in latency to engage, right? But if you go back to some of his like other results, if the timing of this optical stimulation is very critical. So, for example, if he give it at the time of rewards recovery from previous trial, you would not see any change in the latency of the next trial, right? So that makes me think and wonder that whatever is, well, I mean, even though you may reinforce the choice, right? So this is critical. So at the time of side in, when the animal is getting a reward, if you give it a conjunction or like at the same time, if you give it another pulse of dopamine, next time around, the rat is more likely to make the same choice, right? But will not do it more vigorously. I mean, if you define vigor by latency to initiate. But if you give the light pulse right at the moment of light on or trial initiation, you would see this, right? So, I mean, and that's why, I mean, that made us think that there might be two separate functions of dopamine. There's effect of dopamine on learning, reinforcing past history, and then there's immediate effects on performances. Right? So what are your thoughts on that?
Firstly, that's a fantastic question as always. But so firstly, the part where I think I completely agree, well, or 99% of me agrees with you. So basically, the dual roles of dopamine in choice and motivation, I agree with that. All I'm saying, and if you give a reward prediction at the time of choice, it's going to increase the Q value or the net utility of, let's say, the right action versus the left action. If you're always rewarded when the animal, if you always rewarded the right action, then the animal would, if you always stimulated when the animal took the right action, the animal would be more likely to take the right action or choose the right side, even though it's actually not actually getting rewards for choosing the right side. So I agree with that part. I guess the critical part becomes when you're talking about the decay of reward rate after a burst at the time of side in, or after you give a phasic stimulation at the time of side in. So as I showed, if the fast component at side in will still be there, right? And the fast component is still reward rate, but it's largely reflecting the reward prediction error, and that reward prediction error is useful for learning. But if that fast component decays away quickly enough, it's not going to overflow into the next trial. If you take a very slow time component, I guess the difference between the Niyogi et al. Story and I guess the story that you put forward is basically the question of time scale, right? So if we filter those reward prediction errors over a very long time scale, then I'm in trouble. But what I'm saying is I'm filtering it over multiple time scales. So you get these phasic components, but you also get this slow tonic component, or slow, I'm not going to use the word tonic, but you get these slow time scale components in the delight signal as well.
I mean, I don't want to turn this into a debate. I see like the questions coming in. I mean, we've been having ongoing conversation. I'll come back to it, but yeah.
Thank you.
Okay, great. Maximilian Proma Tuzal asks if you have any ideas about the substrate for the filtering. In other words, what biological structures could do the filtering or set the timescale of the filtering?
Right. So there are two questions in there. So like the first, let's talk about the timescale. And Ali might know a lot more about this than I do. I'm certainly not a biophysicist. Or Ilana, you might know this better than I do. So basically, we can think of the acetylcholine or the cholinergic neurons which impinge on the dopamine axons. You can think of them as modulating the reward rate or the time constant of the reward rate. So that's the first question. What is modulating the time constant reward rate? That could be because of the cholinergics. In terms of what is happening, how is filtering happening? Well, the reuptake of dopamine is actually quite quick. Ali, you would agree with that probably, right? So how then is filtering happening on a long time scale? Well, it's possible that D-light is not just reflecting dopamine release. It's showing you the dopamine onto the extracellular from point to point, right? So it's possible that you have a lot more dopamine in the extracellular medium, which is not getting washed away very quickly. The phasic part of dopamine is getting washed away very quickly, and that's not a problem with us with the story. The fast reuptake is leading to the phasic signal being going away very quickly, but the tonic signal might be persisting in the extracellular substrate of the I guess the D1R cells in their accumbens. That's my best guess, but I'm not a biophysicist, so somebody has to do some work on that to figure it out.
Cool. Do we have any other questions? People can, if you, again, you can just, I think we have time for maybe one more question. People should feel free to ask it if they don't feel like writing it down. Okay, well, if that is the end of the Q&A, I just want to really thank the speakers again for giving such lovely talks, and also want to thank Ali and the other organizers for organizing this conference. It's really a great idea, and also fun to learn about this new platform, at least new to me. So just join me in thanking all the speakers and thanking the organizers, and hope to see you all in person at some point. So bye.
Thank you, Lana. Thank you.
Thank you, everyone. So I think with that, we will close this stream. We will go for a lunch break for a few minutes until the next session starts, I believe, 12:45 Eastern time. I mean,